Hello guys, in continuation of our earlier class, I told I dash 2r to be drawn with certain angle with respect to the reference phasor phi. It will be like I dash 2r, and I told if I draw a line opposite to that, it will become what? I2r. Okay, and here also you can see that I2r is lagging my E1 phasor by certain angle what? Phi 2r. Either you can draw first this I2R and you can stretch this later, or if you have drawn earlier I dash 2R, then you can stretch exactly 180 degree opposite to that, so it becomes what? I2R. Either you can go from this point to this point, or either you can go from this point to this point. Anyhow, we get the same thing. Okay, so I am going to stretch again I dash 2R right opposite, that is with respect to this, it will become what? 180 degree. It will be called as what? I2R. Anyhow, we have accounted for this first equation. The only thing remains is the second one, that is E2R is equal to I2R into Z2R. So why I drew like this I2R? Because I need I2R to be shown, right? So I draw I2R. Now coming to this first part, I2R into R2. Basically it's a voltage drop in the resistance, and remember, in the resistance if voltage drop occurs, voltage and current will lie on the same phase. Okay, so that's why I can see that I2R is over here and I2R2 is also overlapping on the I2R. Why? Because voltage, this is I2R into R2 is what? Basically it is a current into resistance, means it's a voltage drop. So voltage drop as well as current lie in the same phase. Why? Because it is occurring in the resistance part. Okay, there is no any phasor difference between voltage and current in the resistance. Both will overlap on each other. Fine. Now coming to the second part, it is I2R into X2, as it's a what? Voltage drop in the inductance, and we know that voltage and current will have phase difference of 90 degrees with respect to each other. So you can see I have drawn I2X2 with respect to 90 degree with respect to what? I2R. So I2X2 due to inductive nature, whatever voltage drop is there, it's occurring in inductance part, and again that is a reactive part. So it lags 90 degree. You can see that it is making at an angle 90 degree with respect to what? I2R2, I2R. Okay. Anyhow, I2R2 is also on the line, the same line. You can call in that fashion also. I2X2 makes 90 degree with respect to what? I2. So now combining I2R2 and I2X2 will give me what? E2R. Okay. You can see combining I2R2, I2X2 will give me what? E2R. From this point to this point it is what? E2R. So it is E2R is equal to I2R into Z2R. Again write in that fashion also, because I2R to I2X2 will give you what? E2R2. E2R is equal to I2R2 plus I2X2. Okay. Either you can draw a line, dotted line can show here, so as to show that R2 plus X2, just like this, how we shown here. Okay. Right angles to that. Any of both will again same phase, not a problem. But make sure you draw I2R2 or the I2R, because it's a resistive drop. I2R2. Next I2X2 is a inductive drop. It's 90 degrees. So summation of this will give you what? I2R into Z2R. Okay. And I2R into Z2R is nothing but what? E2R itself. Okay. So by doing this, we accounted for E2R. Okay. This is done. So this is what we have phasor diagram on no load condition. Basically it's a lagging load. Okay, basically it's a lagging load. Again you can similarly you can draw for leading, and similarly you can draw for no load condition as well. Okay, but this I2R I told you that initially I went with the upper part of the phasor diagram, next with the bottom part of the phasor diagram. Directly took I-2R with certain angle here, without knowing whether it is lagging or leading. But if it is a lagging, means obviously whatever we did initially it was right. Okay. Anyhow, if it was leading, means I2R would come somewhere here, when I2-R would have gone here. Okay. Anyhow, it is all right. We can draw first initially I-2R here. If it is a lagging load, make sure it comes here only in this what you can say first quadrant. Okay, first quadrant it comes in the first quadrant, I-2R, and I-2R will be opposite to that. Okay, so this is all we have with the phasor diagram of an induction motor on certain load. Basically this is a load of lagging. Okay, how we came to know that it's a lagging? We can see I2R lags E1 by phi 2R. Okay, so for the return make it as phi 2R. There you can give that it also. One thing what you can notice here is E1 and E2 are lying on the same phase. Yes, E1 and E2 are lying on the same phase. And always they two things will be opposing your V1. You can see V1 is at the top, it is pointing upwards, but you can see E1 and E2 are pointing downwards. Both the things, what happens, it will always oppose your V1, and E1 and E2 will be always in the phase. Now coming to the no load and block rotor test on induction motor. Now let us see how to conduct no load as well as block rotor test in induction motor. So here we have set up here no load condition. See, it's a basically 3-phase induction motor, and again make sure there is no any load connected to this. And you can see I have connected 2 wattmeter method to measure the no load readings. You can see V0 I0 is also there to measure the no load voltage as well as no load current. So start the motor at the subsynchronous speed. Make sure you apply the rated voltage. Okay, line to line voltages, say around, if it is a 415 volt means apply the rated voltage, and make sure it is all in AC meters. Okay, V0 as well as I0, because since I am connecting a AC supply to this. And again make sure the speed should be subsynchronous, means it should run at the lesser than the synchronous speed. Any of it runs because as it's an induction motor, it runs at the subsynchronous speed itself. And now you can see that power factor will be very less, because as I have not connected load here, so power factor will be less, and efficiency will also be very less. You can see it will be less than around 0.5. Since you can calculate a power factor and all using certain formula. So after performing an experiment, make sure to write the rated voltage V0 as well as no load current, what all the current is flowing here, and similarly write on the W1 as well as W2 readings. Since your motor is running at the lagging load, so obviously what happens, one of your meters will read negative. Okay, one of your meters will read negative. Make sure to take them as in terms of make sure you change either current coil or potential coil so that it reads in the positive, but you have to take that reading in terms of negative. Say if W1 is reading negative, means either you have to change the current coil interchange, or you can change the potential coil. You can change any one, not both. Anyone you have to change. After changing, what happens, whatever the W1 was reading negative, it reads now positive. That positive magnitude value should be taken in terms of negative itself. Okay, and remember that. Okay, and just add them, you'll get what, no load wattmeter reading. Okay, again we know that W0 is equal to root 3 V0 I0 cos phi. This formula you know, and cos phi power factor you can calculate by this formula. Cos phi I0 is equal to W0 by root 3 V0 I0. Okay, V0 and I0 are line values. If they are phase values, means what you can do is W0 divided by 3 V phase I phase, means V0 phase I0 phase. If I am measuring voltage between phase and neutral, any neutral is not shown, line voltages are there, line current is there, so better go with this formula. This is what you get it as no load power factor, and it will be very, very less. Okay, so this IC is equal to I0 cos phi 0 as well as IM is equal to I0 sin phi 0. This you can easily calculate by referring the above phasor diagram which we discussed earlier. And R0 is equal to V0 by IC. How this has come, you can take help of this diagram. Wait a second. Yes, R0 is equal to, we know that the voltage across this is V0. So R0 is equal to what? V0 by IC. Okay, R0 is equal to V0 by IC. Similarly, you can see X0, we know that again the voltage across this is V0 itself. So V0 divided by IM. Okay, V0 divided by IM will give you what? X0. So that is the no load branch resistance as well as no load branch reactance. And we know that power input, that is W0, consists of 3 things. One is stator copper loss, stator iron loss, as well as friction and windage loss. Okay, 3 things: stator copper loss, stator core loss, as well as friction as well as windage loss. Since what happens, copper loss is very, very, very less. Okay, copper loss is very, very less. So what happens, usually the first one is neglected, only the 2 things are considered, that is iron loss as well as friction or friction and windage loss. Okay, so you can see that W naught consists of stator iron loss as well as friction and windage loss. So collectively you can call it as what? Rotational losses. Okay. So stator core loss as well as friction windage loss will give you what? W naught. Okay. No load losses. Okay. This is the fixed loss. So that's why I'm telling we are neglecting a stator copper loss here, as it is very less. Now coming to the block rotor test. In block rotor test, what I'm going to do is I'm going to use the belt arrangement so that I'm not allowing the motor to run. I'm going to tighten it so that rotor doesn't rotate. And we know that RL is given by R2 into 1 minus S by S. If I refer to stator means it becomes RL dash R2 dash into bracket 1 minus S by S, which we already know, which you have done there in your earlier class. And one thing we know that it is block rotor test means what? Slip will be always equal to 1. So if I substitute slip is always as 1 here, so what happens? RL dash will become to 0. So RL dash is 0 because you are blocking the rotor. Okay, this is what given here. R1 is what? R1 plus R2 dash, whereas X1 is X1 plus X2 dash. And when you have RL is equal to 0, RL dash is also 0, so slip is equal to 1. Okay, so this circuit diagram will result into this. And take help of this here. Yeah, over here you can see RL is 0, so this particular part will be 0. Okay, coming to this here, it is very much clear. See, okay, this part is again 0. Okay, because it's a block rotor test, because S is equal to 1. Finally, you can call this as also 0. And finally, what happens? R1 plus R2 dash equal to R1E, and X1 plus X2 dash equal to X1E. Okay, this is what given here. Okay, R1E, X1E. And anyhow, we'll refer the voltage applied as short circuit VSC. And again, what current flows there? Short circuit current. Make sure one more thing, while conducting block rotor test, you never apply rated voltage. If rated voltage gets applied, then what happens? 7 to 8 times that of rated current will start to flow. So make sure you apply voltage in the reduced fashion till the current flowing in the circuit, stator circuit, reaches what? Rated value. Okay. So VSC is the short circuit voltage, IS is the short circuit line value, WS is the short circuit power. So it is equal to, so any of this formula, you know, WS is equal to root 3 VSC IC cos phi. And anyhow, you can calculate the power factor during the short circuit. And anyhow, again we know that short circuit formula is given by I square SC into R1E. Okay. Again multiplied by 3. Why we are going to multiply by 3? Because as there are 3 phases like this, so I'm going to multiply by 3. And ISC is per phase value. And similarly, you can calculate R1E. Okay, by doing here and there. Okay. So this is the equivalent resistance referred to the stator. So Z1 is what? Z1E formula is VSC by ISC. So Z1 is what? R1E plus X1E. So Z1E, this is what collectively called as this. So Z1 is equal to VSC by ISC. Okay. So don't confuse with R1E as well as Z1E. R1 is always with respect to the current, and Z1 is with respect to the short circuit current. Okay. I mean R1 is with respect to the what? Short circuit power, WSC, whereas Z1 is with respect to the short circuit voltage. Okay, make sure you remember this. And X1 you can calculate, very simple, square root of Z1 square minus R1E square. And here in short circuit loss, what happens? Again, it is referred to the what? Copper loss itself, copper loss. Okay, so it includes copper loss in the stator as well as copper loss in the rotor. So collectively, I'm going to get what? Stator as well as rotor copper loss. So WSC is equal to stator copper loss plus rotor copper loss. Okay. And one thing we know that as we are not applying what? Normal voltage during conduction of block rotor test, we are applying what? Reduced voltage. So whatever current flows there, it is not as per the short circuit current. Okay, it's a what? Controlled short circuit current, but it is not the full short circuit current. So how to calculate the control? That is full short circuit current by using this formula. VL is normal rated line voltage, where VS is the reduced short circuit voltage, which we applied in the while doing this. Just apply the formula ISN equal to VL by ISC into ISC. Just putting the values, you will be getting what? Short circuit current at the normal voltage. It will be usually around 7 to 8 times that of rated current. And ISC is the short circuit current at the reduced voltage. This is the rated current which is written on the nameplate of your motor. And ISC is what? Short circuit current at normal voltage applied. This you can only calculate theoretically. We can't do it practically. Otherwise, the motor will get burned. And finally, WSN you can calculate by this ISN by ISC whole square into WS. This is the direct formula. Just remember, where WSN is what? This is a core loss plus stator and rotor copper loss. Okay, just remember this. And WSN is also called as what? Short circuit input power at normal voltage, because as we calculate WSC at the reduced voltage, but WSN is the what? Short circuit input power at the normal voltage.